We are smart. Okay, so today we are going to go through this problem set. You will want to have your work out. We should be able to get through the whole thing. We were able to get through the whole thing in my last class. But just so you know, I don't post my keys for these problem sets. So class is where you're going to get information about whether or not you did it right. All right, so first problem. Not a lot of background information, just some basic statistics. So it says one sample has n equals 4 scores with a sum of squares of 100, and a second sample has a sample size of n equals 8 scores with a sum of squares of 140. If you're going to calculate the pooled sample variance for the two samples, what do you have to do? What do you have to calculate to get there? Okay, so you're going to need to have some sum of squares. What sum of squares do you need? Okay, so you're going to need to know the sum of squares pool. What else are you going to need to know? The degrees of freedom pool. Okay, and how do you figure out sum of squares pool?
Add them up.
Add what up?
Two sums of squares.
The two sums of squares. Okay, so the sum of squares for group 1 plus the sum of squares for group 2. And if you're going to do degrees of freedom pool, what are you going to do? Same thing. Degrees of freedom 1 plus degrees of freedom 2. Right? Okay. So knowing that, okay, knowing that this is how you get the pooled sample variance, you've got enough information to fill out this part of the equation, right? You know that sum of squares 1 is 100. Sum of squares 2 is 140. Okay. So if you add those together, our sum of squares pooled is 240. Good. And then our degrees of freedom for group 1 is 3, right? Degrees of freedom, if n equals 4, then degrees of freedom will be 3. Okay? And then for group 2, it's going to be 7. So now we're adding 3 and 7 together to get our degrees of freedom pool, and that's 10. Okay? So now I'm going to divide 240 by 10, and that's going to give you what?
24.
Okay, 24. So for 1A, the answer is 24. Then you have to calculate the estimated standard error. Okay, that's this one. And the formula to do that looks like that. We know all the values in here now, right? We know that this is 24, right? So you can plug 24 into that slot for both cases. For N1, N is 4. For N2, it's 8. So what do you get for the estimated standard error? 3. Good. Then it says, if at any point, okay, if we're going to go through this, my assumption is that you have worked through all of these problems on your own already, and that you have your work in front of you to compare to what we're doing up here, which is why I'm not writing out every single step on the board. We're double checking to make sure you got the right answer. So if you got a different answer, I'm glad to back it up, go through it to make sure we figure out what went wrong, so that you can make sure you have the right answer and you know where the right answer comes from. Yeah?
I got 3.46.
Okay? So,
I had 24 over 4 plus 24 over 8.
okay? So 24 over 4, 24 over 8. So if we do that math, 24 over 4 plus 24 over 8. Okay, we're doing the square root of that. And then we're going to have, if we do that math, then this is going to be 6 plus 3. Okay.
Yeah, just
24 divided by 8 is 3. Okay. So then we end up doing those together. Square root of 9? 3. Got it? Okay. So please, if you've got something different, let me know. We'll find out where the mistake was, because I want you to have an accurate set of solutions to work with as you study for the test. And you'll notice, on the problem set, I'm not saying, here's all the pieces and parts to do this calculation, because on the test, I want you to have thought about what I need for each step. I am going to ask you, tell me the degrees of freedom, tell me this, tell me that. But you have to know what you need in each case. All right. Now, if the sample mean difference, M1 minus M2, is 6 points, is this enough to reject the null hypothesis for a two-tailed test? And so basically what I'm asking, in order to know if this is enough to reject the null hypothesis, we need two things that we don't have. T observed and T critical. To get T observed, the formula is the mean difference over that estimated standard error. So if I tell you that the mean difference is 6, and we just calculated this estimated standard error as 3, you know that T observed comes out to be 2. Does that make sense? Okay, is that what you got? Your people are smiling, they're like, yep, that's what I got. Yes?
And when we use the 2, we don't have to write positive or negative, just
You do. You have to write positive or negative to show me that you know it's a positive or negative value. Yes. For observed values and critical values for T, I want you to mark the polarity. Mark it to show me that you know. Yeah.
If we just put 2 and not 2.00, is that okay?
Yeah, that's okay. As long as there's no other, this happens to be a whole number, so yeah, that would be fine.
So whole numbers are fine.
Yeah, if it's actually just 2, but if it were 2.01 and you just put 2, that would be wrong. That would be rounding error. Right. Yeah. But yeah, if you just put 2, that would be fine. All right? So what's the critical value
2.
that we need to compare this to? Well, let's see. What's the information we need to figure it out? We need to know, we've got that it's a two-tailed test. Alpha is 0.05. Okay? And what are we going to use? What degrees of freedom are we going to use? Pooled. Okay? We're going to use degrees of freedom pooled, and we figured that out in step 1A, right? Okay? So in 1A, we figured out that degrees of freedom pooled is 10. And so if we're using degrees of freedom 10, alpha is 0.05, for a two-tailed test, our critical value is going to be plus or minus what? 2.23? Yeah? Okay. And which one matters for the purposes of this comparison? The plus one, right? The positive one is the one that matters. Okay? So now we're going to compare our critical value and our observed value. And the one that matters here is going to be plus 2.23. And the observed value we have is plus 2. So the relationship is that. So is this sufficient to reject the null hypothesis? Nope. If we think about it, we think about a distribution. That's the critical value in the positive tail. We've got 2.23. And this 2 value is somewhere right there, which means that it didn't make it out into the critical region, so we retain the null hypothesis. Make sense? All right. So what happens if the sample mean difference is 9 points? Now what changes is this value right here, which changes this value right here. Now what? How does that change the story? Now we can reject, right? Now we can reject. Because now, instead of our observed value being here in the normal part of the curve, now it's out there. So now we've got a statistically significant difference. So just changing the mean difference changes whether or not we get a significant result. We keep everything else the same. Okay? All right? Next question. Do you view a chocolate bar as delicious or fattening? Are those my only options? Can I view it as something else? My daughter views it as disgusting. She does not like chocolate. I do not know how she ended up being my child. No, I do know how. I was there, actually, so I do know how she ended up being my child. But I'm really confused about how the genetics worked on that one. Okay, so there's a bunch of data. You've got that, you know that. So the sample size for men is 6, the sample size for women is 9. The mean for men is 31. The mean for women is 45. The sum of squares for men is 490. The sum of squares for women is 680. All right, so we need to go through all the same steps, right, that we just did, all the same steps to figure out if there's a significant difference in the attitudes of males and females. Two-tailed test, alpha 0.05. Okay. So tell me, just because we've been doing this first, if we know that it's alpha 0.05, two-tailed test, what do I need to look up the critical value? Degrees of freedom what? Pool. Okay, and how do I figure that out? Adding the degrees of freedom for our two samples. Okay, and what are the degrees of freedom for our two samples? For sample 1, for men, what's our degrees of freedom? 5. Do you agree? That's 5. Okay, and what about for women? 8. Do you agree? Okay. So if we add those two numbers together, what do we get for degrees of freedom pool? 13. So if I look up two-tailed test, alpha 0.05, degrees of freedom 13, what do I get for a critical value? 2.16. Okay. So that's my critical value. Now, what do I need to do? I got to go through my steps again, right? Okay, so I figured out, I know this value now. I just figured out my degrees of freedom pool because I needed to figure it out to look up my critical value. Now I need to do my sum of squares pool. How do I get that?
490 plus 680.
Yep, just add up those two sums of squares. So what do I get? What is 490 plus 680? 1170. So 1170 divided by 13 is 90. How you doing so far? Getting it? Right. Now, next thing we have to do, we calculated this. Now we're moving on to estimated standard error. We're going to do the square root. So this is going to be 90, right? Divided by?
Oh, no, the rest.
So that's not degrees of freedom, right? That's sample size. So what is our sample size for men is 6. Okay? Got to remember, sample size for men is 6. Then over here, it's going to be 90 divided by 9. Yeah. Okay. So what value do you get internally for this? 25, right? This value in here is 25 because this is 15 and 10. Okay, so we get 25. What's the square root of 25? 5. Okay. So our estimated standard error is 5. And now we do our observed value. Do our observed value. M1 minus M2, so that's 31 minus 45. Okay, so negative 14. And then we figured out that our estimated standard error was 5. So if we do that math, what do we get for our observed value? Negative 2.8. Okay. Negative 2.8. All right, now, we think about this picture of the distribution again. Now I'm over here in the negative end, right? So this is the negative value. So I'm over here in the negative end. Okay? We've said that my cutoff value for the critical region is negative 2.16. Negative 2.8, is that on the left side of that line or the right side of that line? What's over here? These values are moving towards 0, right? And then moving up here towards a positive end. It's over here. To be in the tail, it's got to be out there. So here's something that I wanted to clarify for the last class. I want to clarify for you too. Up to this point, we've worked with lots of positive values. So when we've been writing out critical and comparing to the observed, we've been writing it out like this. Critical, observed, okay? And we've been writing it out. And if it goes like that, then we say, oh, it's statistically significant. I can reject the null hypothesis. Okay? But this relationship only works for the positive end, right? Where we need the critical value to be on the left and the observed value to be on the right for significance. Okay? That's for the positive end of the distribution. When we start talking about the negative end of the distribution, you have to think the opposite way. Because in order to get a significant result at the negative end of the distribution, I need my observed value to be to the left of the critical value, right? Because there's my critical value right there. I need my observed value to be further out this way. So here we've got 2.16 and 2.80. And that gives us the right relationship to show that there's a significant difference. Because 2.8 is less than 2.16. But in the case of a negative value, that's a good thing. Because that means it's further out in the tail. And that gives us that symbol that we want to let us know that we're talking about a probability that's less than alpha. Okay, you're making a face.
Okay, what if, like, could we just make the 14 positive, or do like M2 minus M1 to make it positive numbers? Or is that
Sure, you could.
Okay.
If you do that, so you could have the mean difference go the other way.
Yeah.
You could. Then what you want to do is make sure that when you describe the outcome of that result, you talk about something being bigger than something else. So in that case, you might say that females have a greater concern about food and weight than men. Whereas the way we did it here, it's men have less of a concern about food and weight than women. So yes, you absolutely can do it the other way if you want to. Just make sure that your description matches your math.
Okay.
So if you show up with a positive value, then you should be talking about something being bigger. You're coming up with a negative value, you should be talking about something being smaller or less. Does that make sense? That way your math matches your words and I understand what you're talking about. It always makes me crazy when people do the math one way and then say it the other way. It's like, just do the math the way you say it so that I understand what you're talking about. Because the math and the word should match. Okay? All right. Yeah, good question.
When we write out the 4-point APA statement, would we follow the sign that way?
So it's always going to be, if it's statistically significant, okay? If it's statistically significant, P is always going to be less than whatever your alpha was. So if you do it this way for negative, to figure out what the relationship is, that will give you the right symbol. Because this is significant. That's a significant difference. So anytime you're writing out in an APA style, if it's statistically significant, if you've got a significant difference, it's going to be P is less than, and then whatever your alpha value was. So if your alpha was 0.05, it will be P is less than 0.05. If your alpha was 0.01, it's going to be P is less than 0.01. Okay? This means that the outcome was statistically significant. If the outcome is not statistically significant, if you retain the null hypothesis, then it will be P is greater than whatever your alpha was. I love how the guy looks at me like, what? I'm like, we're sitting down outside the classroom talking real loud on the phone. Yes?
So for Cohen's or something like this, the mean difference
would be negative, would you take the absolute value?
Oh, you can't come in now. You're late. Yeah, so you all, when you did Cohen's d for this, you would take the absolute value. Yes, because Cohen's d is always positive. Yeah, you got it. Because a negative treatment effect, because we're talking about the size of the effect, not the direction of Cohen's. Yeah, you got it.
So Cohen's d is always absolute value.
Yep, Cohen's d is an absolute value. So even if your mean difference is negative, your Cohen's d will still be positive because you just treat it as an absolute value. Good question. Okay. So, just another note to remind you, if you're looking at a table, like the table from the article, which is going to show up on the test, if something is significant to an alpha of 0.05, you'll see the observed value marked with a single asterisk. If it's significant to 0.01, you'll see it marked with 2 asterisks. And if it's not significant to anything, it doesn't matter, you'll see either nothing or NS or non-significant. So you want to make sure when you see that in tables in papers, you understand that that's what that notation means. Okay. So we talk about computing the effect size for sex difference using R squared. We're going to use our T observed value, right? If I do that, I'm going to end up with T squared over T squared plus degrees of freedom. What kind of degrees of freedom? Pool. Right? The same one that you use for the critical value. Look up the critical value. Right? And what did we get for R squared? What did you get? 38% is what I got. 38%. All right.
How do you know which t to use?
It's always T observed. For R squared, the T in the formula is always T observed, and the degrees of freedom is always the same degrees of freedom you use to look up the critical value for your t-test. Okay. So, if we translate that to related groups, if I ask you to do a related groups R squared, how is the formula going to be different? It's going to be T squared, because that has a T observed too. T squared plus degrees of freedom.
Different.
Right, of the difference. That's the difference in the formula.
For related groups?
Related groups. And what about for Cohen's d? Cohen's d is always the mean difference over standard deviation. So for independent groups, it's typically M1 minus M2 or M2 minus M1, if you want to do it that way, whichever works. Okay, because it's still going to be the difference, so it doesn't matter. The difference between the two, absolute value, divided by some standard deviation. The only standard deviation we have to work with independent groups is the standard deviation that we take from the pooled sample variance. And so you have to know, to get that value, you got to take that standard deviation, you have to take the square root of the pooled sample variance. That's how you get the value you need for the denominator of Cohen's d. That's for independent groups. If you're doing it for related groups, the formula is going to change because your mean difference is that, right? Mean sub d, and you're going to divide that by S sub d, standard deviation of the difference. And we get that by taking the square root of the sample variance of the difference. So you have to know where to get the right standard deviation to use for your Cohen's d denominator. So make sure on your card you've got both formulas or you know how to do it by heart. So you need to have 2 formulas for R squared, 2 formulas for Cohen's d, so that you have the right one for the kind of test you're doing, if you don't remember how to do the modification. All right. So next, we got people classified into 2 categories, type A personalities, type B personalities. Okay. All right. Type A's and type B's. Oh, here. Okay, so we've got our data here. This is an independent samples test. People with type A personalities are distinct from those with type B personalities, so these 2 groups don't overlap. You're either type A or you're type B. You don't get to be both. Can't be randomly assigned as a subject variable, right? You come in with your personality. So because we've got an independent groups test and, the other critical thing, our sample sizes are the same, we can now do an Fmax test. Okay? You can only do Fmax when the sample sizes are the same. Up to this point, the problems we've been doing have had different sample sizes for the different samples, so we haven't been able to do Fmax. But now we have sample sizes that are the same, so we can do Fmax. What do I need to know to do Fmax? What's the formula for calculating Fmax observed?
Variance 1 over variance 2. The smallest.
You mean it's not sitting right there on your work because you wrote this part out? What?
Sample variance over sample variance.
Yes. Got one sample variance over another, so there's which one goes on the top and which one goes on the bottom. The big on the top, right. The biggest one goes on the top, and the smallest one goes on the bottom. Okay, so I'm going to have to figure out I've got 2 samples, so I've got to calculate sample variance for both samples so that I can figure out which one's bigger and which one's smaller, so I know which one goes on the top and which one goes on the bottom. So how do I figure out the sample size for group 1? The type A people.
Sum of squares.
Sum of squares 1 over?
N minus 1.
Over degrees of freedom, right? Yeah. Or n minus 1, right? That's also true. Because the formula for degrees of freedom is n minus 1. Okay. Sample variance is always something sum of squares over something degrees of freedom. Sample variance. All the time. Okay. So I know that my sum of squares is 740 for that group. My degrees of freedom is going to be n minus 1 or 8 minus 1, so 7. So 740 divided by 7 is what?
105.71.
I don't know. Is it 105.71?
Yes.
Yes? Okay. I know the answer over there, but I can't read that well from 10 feet away, so I have to ask. Okay. So we do the same thing for sample 2. What do we get? I have a vote for 94.29, and other people over here who also agree with that. Okay, math by consensus. It works. Well, it's nice to know other people agree with you, right? I mean, it's not like, well, Dr. Darnell says it's the number. Well, I could be wrong, but if 6 other people in the class think that's the right answer, then either there's something horribly wrong with the problem, or you guys are all right. Let's just assume you're all right. I prefer that positive approach. All right, so the larger one is this one. The smaller one is this one. So if I divide 105.71 by 94.29, what do I get for my Fmax observed?
1.12.
I vote for 1.12.
Yes.
Yes? Okay. There's my observed value. Fmax is another one of those things that's always positive. So, okay. And what about critical value? How do I look up a critical value for Fmax? With K, I need to know K, which is the number of samples. which effectively means the number of different conditions. So I need to know K. In this case, K is 2. T for 2, T for t-test, right? 2 samples. So K is 2. Alpha is 0.05. And my degrees of freedom, the one that I use is, I can only do F max if I have a common degrees of freedom, right? Where both of my samples have the same degrees of freedom. And that degree of freedom is 7. So with degrees of freedom 7, and K equals 2, alpha is 0.05, what's my critical value for F max? I have votes for 4.99. All right? That means the relationship between those two is like that. That means I am retaining the null hypothesis. Is that good? Yes. We have an argument for yes. Why is that good? Why do I want to retain the null hypothesis for my F max test? Go ahead. That's right. It means the samples have homogeneity of variance. It means they're similar enough to compare. And that's what we have to know for an independent samples test. They're not so different that we worry they're actually drawn from totally different populations. And we can't compare them. Yes, in the back row.
How'd you get the 4.99?
We looked it up in the table. It's a critical value, so we got to look it up.
To that packet.
The packet. It's in the packet. That's right. Second, it's the one on the back of the t-test table. I think it's called the critical values for F max. Yes. Oh, wait. Yeah, go ahead.
Would you put the positive and negative sign by the critical value or no?
You can. It's always positive.
It's always.
Always positive. F max is always positive. Because it's based on a squared value, and squared values are always positive. Yes?
When it said one-tail test in the problem, that was kind of confusing. So, like, for the X, the F max is the one-tail and two-tail?
It doesn't matter. That's right. For F max, it makes no difference. The only reason that one-tail and two-tail matters is for the t-test. Yeah. Good question. So,
just to make sure, you said when sample sizes are the same, use F max?
you can't, that's the only time you can use F max. So F max doesn't work if the sample sizes are different. Which is why we have the previous couple problems, we've had different samples. The sample for men was different than the sample for women in terms of size. So we can't do F max because it requires a common degrees of freedom for the two samples. And if we don't have that, we can't do it. Okay, in the back, yes?
If you didn't, if it ended up not being good for,
If for some reason it came out the other way.
right,
Yeah.
then you would still run the t-test, it would just show that it might not be significant because the groups aren't similar enough?
If you run the t-test, basically what this is telling you is that your samples are so different from the beginning that you probably got a confound. And remember, our number one priority when we design a between subject study is having groups that are similar enough to compare. And if your F max, if you end up rejecting the null hypothesis for F max, I would actually recommend stopping. Just don't. Don't do anything else. Because if you get a significant result, you don't know what it means because the groups were so different that there's probably a confound. There's something wrong. And it doesn't ever work out that way on a test, you know, where it's actually, so you're like, oh, I don't have to do half the test. So if you actually do get an F max that doesn't work, you're like, oh yeah, I don't have to do this half the test. I would check it. Because something's probably very wrong. Come up and ask a question if you're missing something. Yeah?
Will you directly ask for F max on the test, or will we ever need to know on our own?
If I don't ask you to calculate a specific value, then you, like a test like F max, you don't have to do it. If I say, calculate F max, then do it. If I don't ask you to do it, you don't have to. But, in contrast to that, like if I ask you to calculate this value, pooled sample variance, for example, then you have to know you need these values to get it, and you have to be able to figure out how to get these values to get those values to get that. Okay. So I may not ask you specifically to calculate degrees of freedom 1 and degrees of freedom 2. You're going to have to know you need to get that in order to get this value. But I will specifically ask you to calculate that, okay, on the test. Okay, so we calculated F max. We know we can proceed with our analysis. If we find a significant difference, we can feel confident because of the distinction between type A and type B personalities, not because of something else, some kind of confound in the sample, in the two samples. All right. So now we're going to go ahead and do our t-test, and we're going to do a t-test here. It's again just bing, bing, bing. These steps, right? We're going through these steps one more time. So what do you get for pooled sample variance?
100.
Okay, so for pooled sample variance, 100. Yes, heads are nodding. Okay, 100 for that. And for the estimated standard error, 5, that's what I got, 5. And we get down to t observed. What'd you get? Positive 2.6. I see nodding from the people. Yes, positive 2.6. Good. So if by chance you didn't do the problem before you came to class, you can write down these answers, do your work, and see if you get these answers, because I'm confirming that these are the correct answers. Okay? If you did your work and you're following along, you're like, I got it. Yes. You're done. Okay. So far we've got now an observed value of, you said 2.06, is that what you said? 2.6. And our critical value, did we figure out what our critical value is? One-tailed test, so it's going to have to be a positive thing. Okay, so one-tailed test, did we figure out what our critical value is?
Two-tail?
One-tailed. One-tailed, 0.05. Degrees of freedom pooled, we figured out was 14. Degrees of freedom, 14. Alpha 0.05, one-tailed test. Our critical value would be what? .7.
2.145.
Okay. So we're going for. Take a look. Let me see what you're doing.
Sorry, I'm looking
Yeah. So make sure you're doing one-tailed test. And one tail. Here you go. This column. One tail. So what do you get?
at 1.761.
1.761 rounds to 1.76. Okay. And if we do the relationship. That work? Is that our critical value? Okay. So then do type A's have more frustration than type B's? Significantly more frustration than type B's? Yeah. Type A's have significantly more frustration than type B's, because this difference right here, that represents the observed value comparing those two samples. This is the cutoff for whether or not it's significant. So type A's have significantly more frustration than type B's. Another way to think about it, 84 is a significantly higher mean than 71. Okay, so their score on the test of frustration is significantly higher. 84 is a significantly bigger number on that test than 71, given those sample sizes. And if we were going to write out the APA-style statistical statement, I didn't ask you to do that, but we could do it. What would we write? We would write T 14 equals positive 2.6, comma, E is less than 0.05, one-tailed, and we didn't calculate R squared or anything like that, so we don't have anything to put there. You could do it if I asked you. All right, moving on. a study on 2 independent groups and obtains a t-observed of positive 2.07 with degrees of freedom 28. That degrees of freedom is going to be degrees of freedom pooled, right? That's the degrees of freedom pooled because the clue here is that it's independent groups. Okay, so degrees of freedom pooled. If it's degrees of freedom pooled, what do we know about how many people participate in the study? Well, we know degrees of freedom pooled is degrees of freedom 1 plus degrees of freedom 2, right? And we know that degrees of freedom 1 is the sample size for N1 minus 1. Degrees of freedom 2 is the sample size for group 2 minus 1. So that means to figure out how many people participated in the study as a whole, I need to take that degrees of freedom and do what? Add 2. Because I got it by subtracting 2, so I'm going to get the number that I want by adding 2. So 28 plus 2. Let's try that again. Soon to be graduating college people. 28 plus 2. 30. The enthusiasm is overwhelming. Yes, 30. All right. So 30 people participated in the entire study. Right? And it says using a two-tailed test with alpha equals 0.05, is there a significant difference between the 2 treatment conditions? So I've already given you the observed value. You don't have to do any math. What do you have to do? You got to find the critical value, right? So you got to go look up a critical value with two-tailed test, alpha of 0.05, and degrees of freedom pool 28. So what do you find? We said this is 2.07. That's our observed value. I'm doing a two-tailed test. I'm going to end up with a critical value that's plus or minus something. What's my critical value? 2.048, I hear I'm going for. 2.05. Yes? I'm just checking. People are very quiet. There's people writing stuff down. So I nod for me. Nodding is good. 2.05. Okay. Okay. So the one that matters down here is the positive one. So, is there a significant difference? Yes. There is. And it says compute R squared to measure the percentage of variance accounted for by the treatment effect. All right. R squared. R squared for independent samples right there. So what do we get for R squared? 13%. R squared is 13%. Okay, good. Any questions so far? Yes?
I'm sorry, I was a little confused about the degrees of freedom and why you added.
Okay. So we know that for an independent samples t-test, the degrees of freedom we would report is the degrees of freedom pooled. Okay? You would agree with that? Okay. Degrees of freedom pooled comes from adding the degrees of freedom for the 2 samples in our study. Right? It's independent samples, so we have 2 different groups of subjects, and we calculate the degrees of freedom for each sample independently, then we add them together to get degrees of freedom pooled. With me so far? Okay. So to get degrees of freedom for each sample, I take the sample size and subtract 1. Right? So if I'm trying to figure out from the degrees of freedom pooled how many people were in the study as a whole, I have to add 2 because I subtracted 1 from each sample to get that number. Does that make sense? So if you take the degrees of freedom pooled and add 2, that will tell you how many people overall participated. You don't know how many people were in sample 1 and how many people were in sample 2. You have no idea. All you know is that when you add them together, there is a total of 30 people. All you know is that when you add them together, there was a total of 30. Okay. So, now, tell me why a researcher performs an Fmax test on 2 independent samples, or on 3 independent samples, or 4, or 5. Doesn't matter how many independent samples you have, as long as they're independent. So why would you perform an Fmax test again?
See if they're similar enough to compare.
To see if the 2 samples are similar enough to compare. Right? To see if they have homogeneity of variance. If they do, you can proceed with the analysis. If they don't, then you're worried that the groups are so different to begin with that any significant differences you might observe are the result of a confound or some selection effect or something, not a result of whatever it is you're actually looking at. Why would you not do that on a related groups test?
Because they're already similar.
Yeah, how come they're similar? The same people, right? Or the same rats, or the same whatever. It's the same subjects getting tested over and over, so you can assume homogeneity of variance and not worry about it. It's the same people, or same rats, or same dogs, or whatever. The sample should have homogeneity of variance already, because it's the same subjects. All right. The stimulant Ritalin has been shown to increase attention span and improve academic performance in children with ADHD. To demonstrate the effectiveness of the drug, a researcher selects a sample of n equals 25 children diagnosed with the disorder and measures each child's attention span before and after taking the drug. The data show an average attention span of 6.8 with a standard deviation of 5.5. Now, in this problem, I will tell you that when I did this, I did what you were talking about before, which is go for the positive value because I wanted to show an increase in attention span. So I took the experimental condition, which is after they took the drug, and subtracted out the control condition, which is before they took the drug, because that's your baseline. So that 6.8 there represents an increase in attention span. That's how much better. That's how much better they got over the course of the study. Now, if you do the math the other way, that's fine too. The numbers will be the same. You might have a positive or negative value somewhere else. But we can go ahead and go through all that math now. Okay. So, first question. Is that result sufficient? Is that mean difference of 6.8 minutes, that improvement of 6.8 minutes over time, sufficient to conclude that Ritalin improves attention span if we do a one-tailed test with alpha of 0.01? And now we're doing a related groups t-test. Right, related groups, same kids, just at 2 different points in time. So now some of our formulas up here need to change, right? We got the wrong formulas up here, because this is all for independent groups. We need related groups formulas up here. So typically, I give you some measure of variance. So how do I get that value? How do I get get that? I'm missing something in here.
The square root of variance. I don't know.
Well, I need something. I mean, these are the equivalents.
Would you square the standard deviation?
Yeah, if I take that standard deviation and square it, that'll work. Because remember, variance is standard deviation squared. Okay. What do I need to calculate this SMD thing? That estimated standard error. What's the formula for that?
You can do standard deviation over divided by square root of ND.
Okay, so there's two different ways I can get it. I can either get it with the standard deviation over the square root of the sample size, or square root of the sample variance of the difference over the sample size. Either of those formulas will get me the answer. We take everything in, we're always talking about the difference scores when we do this kind of t-test. So I refer to it as a sample size of the difference because it's the number of scores in the set of different scores, the number of scores in that set. So sample of the difference. It's also the same thing as the number of people that you tested or the number of subjects that you tested, but it has to do with those different scores. How many different scores do you have? What if I gave you sum of squares of the difference? What would you do? How would you get the number you need from sum of square?
Divided by the degree of freedom.
Yeah. So another way to get that might be sum of squares of the difference over degrees of freedom of the difference. So you should be able to get the number you need from whatever I give you. If I give you some part of variance, you need to be able to figure it out. Okay, so if we calculate, figure out some way, we figure out what we need, either we take the standard deviation and use it, or we calculate the variance and use it. What is my estimated standard error of the difference, or SMD? What does it come out to?
1.1.
1.1. Comes out as 1.1. SMD comes out as 1.1, this value. Yes? Good question. How will we get 1.1? We have to use these values so we know what the standard deviation of the difference is. That's in the problem. What does it say in the problem?
5.5.
So the standard deviation is 5.5. And then we divide it by the square root of the sample size. The sample size is 25. If I take the square root of that, it's going to be 5. So if I take 5.5 divided by 5, I get 1.1. There you go. That's where it comes from. Okay, so I've got SMD is 1.1. If I do my t-observed, I've already given you that the mean difference is 6.8. So if I take 6.8 and divide it by SMD, which we said is 1.1, what do I get? Positive 6.18. Yep. And did we figure out what our critical value was already? I don't know, is it? 2.49? Yes, it is. We're doing a one-tail test with alpha of 0.01. So we've got 2.49. That's our critical value. And our observed value is 6.18. So we can reject the null. Yep, reject the null hypothesis. Cool. So, is this result sufficient? Yes. The answer is yes. You have to do all that math to be able to say yes. All right, then we do R squared to calculate the effect size of the drug, and what do we get? 61%. That's huge. In other words, Ritalin has a monstrous effect on children's ability to hold their attention. It really, really helps these kids. Big treatment effect. Okay? So if we summarize the results in a sentence, what groups are we comparing in this study?
Children with ADHD.
Children with ADHD, but we're comparing them at 2 different points in time, right? So we're comparing children with ADHD before they take Ritalin and after they take Ritalin, right? So after they take Ritalin, they have what? A significantly better attention span than they did before they took it. Children with ADHD have a significantly better attention span after they take Ritalin than before they took it. And if we do the APA style statistical statement, that's going to be T what? 24? Yep. 6.8, comma, what? P is less than 0.01, right? Because our alpha is 0.01, right? One tail. R squared equals 61%. Yep. Did you get it? All right. How many of you are doing better than you thought? No, you're not?
A lot of weird arithmetic errors.
But are you finding any commonalities? Like you tend to make mistakes in this one place? Or is it just not being careful?
Just not being careful.
Okay.
Not paying attention.
So we got to pay attention. Ritalin. Apparently we'll do it for you.
Yeah, not taking a value correctly. Okay.
So it really helps to write every single step out so you can find where the mistakes were. And you want to find out if there's a common place where you make mistakes, because that may be where you want to take a note, put a note on your card, like put that in red or something, like don't forget, use N here, not degrees of freedom or something like that. All right. And again, someone asked in the last class, will I give you the little charts telling you what's a small, medium, and large effect of Cohen's D and R squared? The answer is no. That's something that needs to go on your card. Okay, so you need your formulas on your card. You need your size of different treatment effects on your card. Anything else you want to put on your card? You want to put little diagrams. You want to put positive messages to yourself. You want to put passages from your personal book of scripture. Whatever works for you. You can put anything. I've seen everything. I've had people say, you're doing this for so-and-so. And I said, who's so-and-so? Oh, that's my son. That's why I'm here. I'm doing this for him. So even though this is hard, put whatever on that card you need. Smiley faces. The only thing you can't put is like, Dr. Darnell, you suck. Or anything like that. Totally not. Okay. Then I get sad when I look at that card. If it helps, no. Because putting Dr. Darnell, you suck, does not help you in any way. It's only intended to be mean. Be nice to your hardworking, peacock-haired professor. Yes?
I was gonna say, I'm gonna make a video on like Javier's pro tips on how to make a good test card.
I like that.
So be on the lookout before Thursday. It should be out there. It's gonna be pretty cool.
Yeah, try to get it out tonight if you can.
Yeah.
Because they're gonna be working on the next couple of days. Yeah, pro tips. Yeah, I told him, you can make a note card pro tip thing, because yeah. And if you have pro tips you think that Javier should include, things that really work for you, I suggest that we'll make note card pro tips. All right. So now we are on the last problem. Oh, look, we're back to old people and blueberries. Okay. So the researcher wants to determine whether taking a blueberry supplement that has antioxidants facilitates cognitive performance in elderly adults. So same thing, pre-test, post-test, taking people before and after they get the treatment and comparing their performance on the same test. Okay, exactly the same setup, just different subjects, different manipulation, right? But same idea. All right. So now I've given you the mean difference, and now I've given you some squares instead. Okay? But same same idea. We got to go through these same steps for related groups. Now we're doing a two-tailed test with alpha 0.01, and we're trying to figure out whether this supplement causes significant difference in participants' performance. And 7.4 here again represents their performance at the end minus their performance at the beginning. So we're taking the experimental value and subtracting out the control value to show improvement over time if there was improvement. And this is a positive number, so that suggests improvement. That their cognitive performance actually got better after taking the supplement. Now I have to find out if it's just a numerical difference or if it's a statistically significant difference. So I've got to calculate these different things. So this time I don't have standard deviation or sample variance. All I've got is sum of squares, so I'm going to have to figure out degrees of freedom of the difference so that I can calculate my sample variance of the difference. So I know my sum of squares of the difference is 240. What's my degrees of freedom of the difference going to be? 15, right? Because my sample has 16 members, which means I'm going to have the degrees of freedom 15. So 240 divided by 15 is what? 16. Okay. So now that I know my sample variance of the difference is 16, I can use this version of the formula. So that's going to be 16 over 16, which means that my internal value here is 1, and the square root of 1 is 1. All right? So my t observed is my mean difference over my estimated standard error of the difference. So I told you the mean difference is 7.4. We know the estimated standard error of the difference is 1. So 7.4 divided by 1, positive 7.4, right? So my t observed is 7.4. Now I need to know, I need a critical value. Yes?
All right, so is degrees of freedom difference always going to be the same number as n?
No, degrees of freedom of the difference is going to be n minus 1. Degrees of freedom is n minus 1.
Okay.
That's going to be n minus 1.
Okay. Oh, no, sorry.
15. It just so happened that for this particular problem, this value and the sample size were the same number, 16 and 16. Just turned out that way for this problem.
Okay.
But our degrees of freedom was 15 here. Did you get that?
Yeah.
15? Okay. And our sample size was 16. It also turned out, just by freak accident, that our sample variance of the different scores was also 16. Okay, so we figured out that our t observed is 7.4, positive 7.4. What's our critical value if we're doing a two-tailed test with alpha 0.01? Okay, what is my critical value? Two-tailed test? 2.95. Okay, so the one that matters here is going to be my positive value. And that's looking pretty significant to me. I'm going to reject the null hypothesis. Right now it says compute Cohen's d to measure the effect size of the treatment. To get Cohen's d for related samples t-test, we're going to take the same thing we used in the numerator for the t-test and divide it by the standard deviation of the difference. How do I get this value from what I have? Take the square root of what? How do I get? I have to calculate that somehow. That is the standard
For your
deviation.
sample variance.
And yeah, and you take the square root of the sample variance of the difference, right? Take the square root. So we figured out that our What was our value, 16? Was our sample variance of the difference was 16, is that right? Okay, so that means the square root is 4. Okay, so our standard deviation is 4. That means that our Cohen's d is going to be 7.4 divided by 4. 1.85, is that what you got? 1.85? Okay, is that a small, medium, or large effect? Large, very large. Okay, so now we summarize the results of the study in one or more complete sentences. So what groups are we comparing?
Before and after supplement.
Before and after supplement, right? We're comparing elderly adults and we're before and after they take a supplement, and what do we notice about their behavior?
Their cognitive performance.
Okay, something happens to their cognitive performance. That's what we're comparing. And what happens to it? It gets better, right? And it gets significantly better, right? So the cognitive performance of elderly adults gets significantly better after they take a blueberry supplement for 2 months. Right? Or if we compare the cognitive performance of elderly adults before and after they take a blueberry supplement for 2 months, we see a significant improvement after the treatment, or something like
You
that.
have to include the fact that it's for 2 months.
You don't have to, but that is, I mean, what you're comparing is people before they took it and people after they took it for 2 months, technically. I mean, you just say, don't want to make it sound, you just had to pop it one day and all of a sudden they're smart or something.
Gotcha.
One day of blueberries and all of a sudden, one Yoplait blueberry yogurt and you're just done, All right, and then we do our APA style statistical statement. And that would be T. What's going to go in our parentheses? 15. Okay, equals
Positive 7.4.
+7.4.
P is less than 0.01.
0.01.
2 tell.
Okay.
D equals 1.85.
Yep. All right. You guys are ready for lab. You're ready for 6 new problems. Let's see if you can rock these out in 2 hours. Anybody have any questions before I send you off to get a snack and then off to 2 more exciting hours of T-tests? Doesn't get any better than that. Yeah, it does. It really does. Graduate with it. You don't have to do a T-test by hand every year. Unless you teach this class, and you get to do this
Grad school.
SPSS.
No, let me tell you that what we cover in 3510 and 3530 in terms of math is the first half of the first semester of graduate school stats. There's 3 semesters of stats in the grad program, and what you guys cover in 3510 and 3530 is what you cover by the midterm. So everything we do in this class, 3510 and 3530, is what you would do by the midterm of stats 1.
See, lied to us.
I'm not lying to you.
No more stats.
No, I'm just saying there's no more hand calculated t-tests. Because you'd be calculating t-tests, you'd be learning more about using software and stuff, but you're doing way more complicated tests that nobody calculates by hand. That we'll even get to tests in this class that we will not calculate by hand. There's no point, no one ever does it. All right.
That really helps me on the last test. The study session,
Really want to know.
Yep. There's lots of cool programs that will do those amazing things.
you want to know, like how to write out, you know what I'm saying? If you know how to write, the 5 for an alternative problem, then you know how to sum up yourself, you know what I'm saying? Because as you can see, she has that like 5 common problems, so it's definitely the middle exam, you know what I mean? But I'll show you, I'll do that on the video, like what's put in your call, like what's always in your exam, you know what I'm saying?
No, that's good.
Okay.
Now you know.
All right, cool. I'll see you tomorrow.
Yeah. Hey, what's up?